In October 2022, this Canadian company sent a giant vacuum cleaner 4 kilometers down into the cold, dark depths of the Pacific Ocean. 3 years later, an American startup launched this tiny spacecraft towards an asteroid far into the empty void of deep space. Both of these companies were looking for essentially the same thing, the next big source of raw materials that could spark a modern-day gold rush. Because all of these EVs, solar panels, and batteries that we're building need expensive metals like cobalt, platinum, and nickel. And right now, we're mostly getting them like this. So what did these guys find, and which one could win the race? The metals company was looking for these little rocks called polymetallic nodules. They were first discovered by the Challenger expedition in the 19th century, and they're found on the bottom of most major oceans. In the 60s and 70s, work began on mapping out how much of these nodules there are, and the biggest known deposit quickly became clear: the Clarion-Clipperton Zone, in the middle of the Pacific Ocean. It holds more than 21 billion tons of them. They contain valuable metals like nickel, cobalt, and copper. Each one only has a tiny bit, but together, it's estimated that there's more than 3 times as much cobalt down there as there is in all known reserves up on land combined. And that's just the nodules. There are also ferromanganese crusts and seafloor massive sulfides, which are geologic formations that contain other valuable metals like zinc and rare earth elements. But what about deep space? What they're looking for is something called a metallic or M-type asteroid.
What it really is, in layman's term, is the inner core of a planet. It's the same as Earth's core, and because of that, we see extremely dense materials in them.
Matt Gillich is the co-founder and CEO of Astroforge. We know these asteroids exist because fragments of them land on Earth as metallic meteorites. But no one is 100% sure of what they actually contain out in space.
And the reason we're not 100% sure is we just haven't been to a lot of them. Like, sure, we see the ones that hits Earth. We have a classification here. We do a lot of studying and bulk analysis, but we haven't visited a lot of them in space.
And Astroforge is betting that those rocks out there contain a huge amount of valuable metals.
The number one thing being that we're going after are what are called the platinum group metals, right? This is a grouping of 6 elements that are worth a lot of money on Earth today.
Astroforge says one M-type asteroid alone could supply Earth's platinum needs for 200 years. Of the million or so asteroids that we know of, NASA's database classifies only 38 as M-types right now. But NASA's currently sending a spacecraft to an M-type asteroid called Psyche. It's set to arrive in 2029, and it's aiming to collect images and data that could help us identify many, many more. So while there's a lot of stuff sitting on the bottom of the ocean, the long-term potential of space mining could be far greater. Getting to them, though, is a different story. In 2025, Astroforge strapped their robot to a Falcon 9 rocket and sent it off towards an asteroid they think might be metallic. The plan was to take photos of the surface of the asteroid, but within hours of the mission beginning, things went south fast. Communication with Odin broke, and the spacecraft was lost, drifting away into deep space. Astroforge doesn't know exactly what happened. They didn't give up though, and are planning their next, even more ambitious mission. But the Odin mission is another example of just how difficult asteroid mining will be to pull off. The first challenge is picking the right target. In 2018, NASA's OSIRIS-REx traveled 2 billion kilometers to visit the asteroid Bennu. What they found when they got there was basically a pile of rubble, loosely held together by its own gravity. When the spacecraft touched down to collect a sample, it sank straight in, far more than expected. That means even if a company did reach an asteroid, it might not be solid enough to actually mine. Astroforge has a plan though.
There's a whole bunch of different ways to land on a small body. There's grappling techniques, people have tried to launch in claws or do other things, and those are all possible, but they're complex. Only one that I think we're capable of doing as a company is with magnetic feet. So these asteroids are primarily nickel iron, which means they're magnetic, which means we can stick to them with magnets.
Once they're on, the mining itself starts. On an asteroid as small as the one Astroforge is targeting, there's little to no gravity. Matt wouldn't say how they plan to mine any asteroid they get to in the future. But in the past, they've demonstrated using lasers to melt the surface of the rock down. Then
we refine the material. So we sit there on the asteroid and we process the material, and we essentially remove the iron and nickel, right? What we're going to be left with is really, really high concentrations of the platinum group metals, and that's what we bring back to Earth to sell.
Mining the deep sea, however, would be much easier. In fact, it's already happened. When all those nodules were discovered lying around in the 60s, there was a massive rush to become the first company to tap into this new resource. In 1970, the American company Deep Sea Ventures became the first to successfully test a mining system on the ocean floor and bring those nodules back. A few other companies and governments tried to make this new and exciting mining resource work commercially, but there wasn't much of a market back then for the metals inside these nodules, and the interest in deep sea mining died off when the United Nations began putting brakes on the industry. We'll come back to that later. Now, all that deep sea mining technology is getting a second life. First, TMC says their vacuum cleaner is sent down to the bottom of the ocean, connected by a flexible hose to a long 4-kilometer pipe to a floating platform above. The nodules are scooped up along with the top 3 to 5 centimeters of sediment that they're sitting on the ocean floor. A rotating hopper inside separates the nodules from most of the sediment, which is immediately released behind the vessel. The nodules and remaining sediment are then sent back up to the surface platform using compressed air, where the rest of the sediment is separated out and released back into the mid-level ocean. What's left are the mineral-rich nodules that can then be sent off for processing and refining. So unlike deep space mining, the technology involved in deep sea mining has not only been invented, it's already been tested and is ready to go. That also means we've been able to start seeing just how much it affects the environment down there. Trying to understand what is happening 4 kilometers deep in the ocean is not easy. No light reaches that far down. The water is near freezing. The pressure from all that water above is about 400 times more than on the surface. But when we look, what we see, against all odds, is a lot of life. In the years leading up to the metal company's 2022 trial run, scientists collected samples from a small section of the Clarion-Clipperton Zone, a huge area with the width of the continental United States. They found 788 species of macrofauna, little tiny animals that live in the sediment on the ocean floor. They're important because across its massive depth of thousands of meters, much of how the ocean works is interconnected. Animals travel up and down massive distances every day, bringing nutrients and carbon along with them to be eaten or stored elsewhere. So, damage to one level of the ocean could have much wider effects. When scientists looked back at the location of the 2022 trial, they found that mining had decimated the biodiversity nearby, dropping the number of macrofauna by 37%. And things take a very long time to recover down there. When scientists went back to another, much smaller test site from 1979, they found that the damage from that test was still pretty much the same 44 years later. But there's still a lot more to learn about what's going on at the bottom of the ocean. And some researchers point out that while it could be damaging to ocean ecosystems, we already know how devastating mining on land is to the environment.
In deep sea mining, you do not have any direct communities which are going to be impacted, human communities. You do not have displaced villages. You do not have the risk of tailings dams that may collapse and you have downstream impact.
That's Salim Ali, an academic who's researched the environmental and social impacts of deep sea mining.
On the social side, the direct negative social impact that we associate with terrestrial mining is absent with deep sea mining.
But while the debate over whether deep sea mining is better or worse for the planet continues, everyone seems to agree that sending rockets out to mine asteroids is definitely better. Let's take platinum, for example. The metal is extremely rare on the Earth's surface. Even when it's concentrated most highly, such as in the South African mines where most of our platinum comes from, there's only 2 to 6 grams for every ton of material mined out. That means it takes a massive amount of CO2 to produce, about 40,000 kilograms per 1 kilogram of platinum. M-type asteroids, however, could look very different. The concentrations of platinum are thought to be anywhere from 10 to 50 times higher, making it much easier to find than down here on Earth. One study found that the CO2 emissions from asteroid mining would fall from 40,000 to only 150 kilograms per 1 kilogram of platinum, with most of that coming from rocket launches. And the best part? No downsides for the actual place that's being mined.
Here's the reality. I can pollute the shit out of an asteroid. Nobody cares. There's 10 million of them, and there's no people living on them. There's no animals living on them, right? There's no infrastructure here. Like, let's go keep this little blue marble safe and secure and sound, and go exploit the kind of rocks around us that nobody cares about.
So there's still a lot to learn about the environmental consequences of both approaches. But for now, space mining seems like the safer approach. But before any company can start mining an asteroid or vacuuming up big sections of the ocean floor, they need to answer some big questions about the finances of it all. Both of these industries are completely new and untested, so they'll need to prove to investors that they're worth taking the risk. For deep space mining, that means investing in the huge upfront cost of a space mission, and waiting for years for any returns, with the added danger that anything mined could just get lost in space. Deep sea mining is more predictable, but it would also need to compete with other offshore mining operations here on Earth.
The metals company says in their project analysis that it's a 28% rate of return. Offshore oil and gas kind of gives you the same.
That's Ian Lang, an economist who writes about where and how we get our mineral resources.
If I'm interested in some sort of, let's just say, non-terrestrial resource extraction, just go to offshore oil and gas, right? It's the same returns and clear legal environment.
That legal environment is the last big question both of these approaches have to face. Both deep sea and deep space mining would mostly happen far beyond the borders of any nation. Is that okay? Well, it's not really clear. The International Seabed Authority, or ISA, is the UN body responsible for the resources on the ocean floor, which are defined as the common heritage of humankind. They get the final say on who is legally allowed to mine where in international waters, and are supposed to ensure that any resources mined are distributed equitably among all countries, including those without access to the ocean. But the backlash against deep-sea mining's environmental dangers has stopped them from publishing the final rules on how to safely mine that would make the industry official. Over 40 countries have now called for a pause on deep-sea mining, while we learn more about what the environmental effects will be. Until recently, TMC was waiting for those rules too. But in January, the US, which is not a member of the ISA, created its own system for giving licenses to miners. And TMC now thinks it could have a permit to start mining by early 2027. Deep space mining faces a pretty similar situation. The only international framework that exists is the 1967 Outer Space Treaty, which prohibits any nation from claiming ownership of celestial bodies, but permits the use of space resources for all of mankind. That sounds a lot like the policy which has stalled deep-sea mining so far. And now, a few countries, including the US, Luxembourg, and the United Arab Emirates, are also taking matters into their own hands, and have passed laws allowing private companies to own the resources they mine in space. But before we all get started on the sexy sci-fi stuff, we have to mention the less sexy but much more achievable option of recycling. One study estimated that there's a comparable amount of cobalt and nickel, and way more copper, between unrecycled e-waste and the deep sea. But as technology expands and humanity's needs grow, these hidden minerals will always be sitting there, just beyond our reach, waiting. So, will deep space or the deep sea supply humanity's need for resources anytime soon? It seems that despite the environmental risks, deep-sea mining companies like TMC have everything they need to get started, so we'll almost definitely see that happen first. But in the long term, the almost limitless potential of asteroid mining and its minimal impact on the environment makes it the more promising vision of where humanity can get what it needs. So which one do you think is a better prospect for powering our future? Let us know in the comments below, don't forget to subscribe, and check out dw.com for more stories like this.